So, I'm here to talk about something rather simple. It's a analog style of light photon computer conversion to a electron transistor with a slight bit of memory through an oscillatory string, or not string, what would you call that, a cable effect, that can push, it releases a photon upon its transistor, processing its transition, blah blah blah. Point is, it's a CPU design. Okay. So what is a good way to describe this? So we're going to take in photons, like fiber optics. We're going to give it a spin, directionality, a polarization, and a wave frequency. As a result of doing this, we gain a massive amount of bandwidth and memory attached to it. We're going to put it above because it doesn't really produce any real heat as a result of that. Very little. It'll mean nothing. And push it through a conversion, analog computer style converter, into a separation, a bifurcation of a electron and a light wave. Okay, so the light wave gets split back into electron, one into it's standard light. All right. Now the electron conversion is actually going to go into memory that's stored next to the transistor, which is just a very high frequency oscillation, like a transistor, but not a transistor. We're not trying to actually have it do anything except store within the hertz frequency a bump of a sine wave, which will equate to a 1 or 0, depending on how high or low. And the AC that is going back and forth incredibly fast will mean that I can store large amounts of data. And in fact, the higher I make that oscillation frequency, the better I can have that transistor on one side and another side both have memory. What is this memory for? This memory is to check, after calculations have been done with the bifurcated line of the wave frequency that's got its polarization and everything, that will then go into a photon quantum tunnel transistor spin effect. So bear with me. This one's a bunch of complicated stuff that most people tend to get really I don't know what that means. Okay. So, a photon can be quantum tunneled and directed its quantum tunnel through an excitation field, and also likelier to quantum tunnel to a given area. As a result of that, I can create multiple different versions of transistors in one transistor. But the photon, because it goes and quantum tunnels to that side, can create a spin effect, which creates a electromagnetic field effect, which then that electromagnetic field effect drops resistance on that side of the transistor and allows more electricity to go through. That more electricity then gets pushed into creating a photon coherented beam. The coherented photon beam, which is a laser, travels down its fiber optic path, changed into its relative information. Before it's allowed to go pass into the photon, it has to do a check. It has this memory on the oscillating cable. This oscillating cable, AC frequency, very high oscillating AC frequency cable, allows for that to be checked as upon this photon being pushed through and then quantumly tunneling onto the transistor to create this spin effect on the other side to drop resistance and bump up electricity. It manages to make a check for the past. Like, does this information, can it be feasible to have been created from this previous information that we have here? And that's what you use with cache, which is going to be an electron cache. Okay, any cache that is light-based is not very easily made, and we're not looking to make easily made caches. Instead, it's more of a filter-based system of, hey, so this electron during the bifurcation process was placed here and it allowed for these series of digital informations to be used as it travels back and forth. This creates this setup of a filter on the other side, okay, which is effectively an angling as a result, mirror, if you will. Which isn't a filter per se, but if you're unaware, that means it can go through that side with the photon as a result of that electricity going through on the oscillation, and then the photon creating the electricity jump, creating the transistor effect, allows for the mirror to properly place itself to allow for it to go into the fiber optic line, thus creating a check, was this the correct information before, that could be used as a result to make this, let's put it this way, it's an algorithm effectively, using the memory in the past, and because quantum tunneling is extremely sometimes noisy, even though we're in a very, very small space creating this effect, I don't want it to go awry. And so by utilizing the information as a encryption key, then it allows for, once the transistor has gone through, that it actually could have made that calculation through the transistor to allow for it to move on to the fiber optic line on over to the next series of calculations, which of course still has its bifurcation methodology, amplification methodology, which isn't necessarily as necessary as you might expect. But the point is the information that came in on the analog style of mirrors and bifurcation or separations of information to the various transistors that we need to hit, which of course fiber optic glass, if you're unaware, or other amazing ceramics, clear ceramics, are extremely proficient at taking heat away from things. They're very conductive in terms of their heat potential. So, just putting that out there. Alongside of radiation of heat, which is IR, we can reflect that with a tube, effectively, on over to the heat spreader, heat sink at the top. That also encases the analog style top piece for the light waves to go into the transistor area, to now no longer be interfered with these electromagnetic radiation waves, hopefully at all. Now, as a result, that also still allows for it to transfer its heat really rather efficiently and gain an advantage as a result of that information coming in being much faster. And it's in its own right is a version of cache. So as it comes in, it's able to just pass it through as fast as an electron, which really is an electron. It's a photon quantum tunnel to an electron event, which is the transistor, which is I call it a weird type of transistor. I don't know what type of transistor that would ultimately be. A QT transistor, because a quantum tunnel transistor. It's a QT field effect, so a QT FE, a QTFE transistor, quantum tunnel field effect transistor, which I feel like is a reasonable claim. We already have transistors that currently do have field effects. They're called MOSFETs. And photon to a field effect is not impossible. We actually do use that for creating spin in quantum computers to allow for the spin to create a photon as it collapses from being a spin into a field effect that releases a photon. I'm doing not that because I'm not trying to do a superposition. I don't want to do a superposition. I just want to do a spin effect. A photon will resultively create a spin effect as it quantumly tunnels and it affects the area of the transistor that I'm looking for it to go to, which of course broadens the bandwidth capacity of each and every single individual transistor, making it so I can make and or if thens, exclusives, and so on. It just needs to be layered appropriately and have the quantum tunnel effect be excited correctly with the right charge and electromagnetic fields as it's moving through, which allows for the wave to collapse its polarization and spin and directionality that we have going on, thus creating an informational exchange during that change. That informational exchange collapsing during the quantum tunnel effect and then affecting the spin is as a result of where it goes to is a way to create a memory into the quantum tunnel event, which also alters its potential area of where it will land. With those two combined, which is technically three at this point, because you have one on this side, one on the other side, which are your field effects, and then you have this one, which is collapsing and then allowing it to tunnel, because you're using that energy as memory energy to allow to help the tunnel event occur, creating a much greater bandwidth capacity. And the photon then allows for a interactional exchange, most likely through, I would imagine, a heat effect spin. As energy is transferred during the quantum tunnel, it loses quite a bit of its energy, but it should still have a wave frequency that is able to impart a version of heat, which will help a spin effect occur. If it's not a heat, then I would imagine it would have to be some sort of an electromagnetic interaction, potential energy to electromagnetic conversion, potential energy situation. Anyways, point is, what it manages to do is once it checks it will take the original information and it has another check after it's gone through all of the transistors that it will go down for the logic gate matrix it's going to take. And then it'll have the original information that sets up its fiber optic line that says, oh, this is trying to tell it to go over here, and it will not allow for it unless it has done calculations that mean it has the ability to then pass through, which is a way to correctively error correct. You know what I mean? Like it's an error correcting technique. So that way it doesn't happen to allow for a problematic noise environment issue, and then cache is of course something different, which is a storage of regular series and sets of values given inside of the oscillative frequency, which when they're really, really small, you can oscillate incredibly fast. Gigahertz aren't really a problem at that point. In fact, the reason why I'm using that technique is because the electrons are slow moving through silicon, and photons are much faster as a result of this effect, and so those are only necessary for when the transistor is needing information, which as it goes through its analog setup of a computer, which does things much faster, because I don't need it to do anything other than set up the information it needs at any given time towards any of those cache areas and checking information. And so that's all I need. That's all that's necessary. As a result, I have error correcting, cached, quantum tunnel field effect transistors. The point is, though, they'll go through a pin system that will then convert it over to RAM and for your GPU, and they'll go through, which are just fiber optics laid through motherboards, and then same thing for HDMIs and DVIs, display ports, so on. My point for this was to remove that bottleneck of electron problems. See, electrons are slow for a type of setup for a computational CPU like this. It can be readily made very soon. It wouldn't be very difficult utilizing current technology with photolithography and layering it to have this be on the market within a few years to maybe a decade at most. Now, the point is that it will send it fiber optically over using, again, that spin, directionality, polarization, or multiple polarizations with multiple bandwidth frequencies to be split again into an analog style computer matrix, which isn't really an analog. It's an analog computer, but it's not an analog matricey. I guess it's a little bit like a matricey because we have a logic gate matricey. Anyways, point is, it's to split it off into the various pixels on a display, and then to have an amplificatory small amount of electrons. Effectively, as a photon goes through, it's going to bump into this material that will then, like with night vision glasses, elicit a increase of other photons that will then go into a quantum dot and small nanocrystal amplifiers. As the photons hit the amplifying crystals and the quantum dot, it then gets filtered out as that color for your red, green, blue. You only need a very small amount of electricity to elicit a greater amount of photons from the night vision goggles style of photon amplification, and then the crystals themselves are also passive, and so you don't really need a amplificatory process with electricity. Photons will just be created as long as you properly diffuse the crystal quantum dot combo hybrid. You get a proper, what would you call that? The quantum slit experiment, where as it goes through, it diffuses, and so then you can coherently allow for it to travel more directionally, but then have it blend, which is kind of what our eyes will do, which is a Gaussian sort of style of blur naturally. And it will work much more realistically to our eyes to be as if it's, seen through light going through atmosphere, which is a very good deal. But then there's also other ways of just doing that with the outside of the pixel being more of a focal coherenter, and so as that Gaussian blur occurs in the inside of the outside kind of box, which is coherented light, it kind of reflects and bounces around and creates a more diffused, more accurate style of light to us, because it's reflective, and that's how we see light. Not shunned directly at us, but diffused, but accurate, and not polarized, but coherented towards us. Coherented. And that's a very simple technique that uses very little energy to be able to use maximal effect of computational power and light-based reductions in time until information is received, which is a very good technique. I don't care what you think about the reflectivity coherented quotation marks style. The point is that is very roughly kind of what that ends up being. So there you go. And it does work. It's a very simplistic design. It was a way for me to get away from having to need an extra cable, because I can run the fiber optic together with in fact, okay, so how to build the display is a coil railgun. Quotation marks, coil railgun. It's a plasma. We're creating a plasma that we're then firing at a substrate that is negatively charged, like powder coating. And then we create an elemental style of 3D printing with plasma that allows for the crystals, the electricity lines, the photo quantum dots, and the photo amplification crystal, the crystal being the coherenter / diffuser sort of thing, lenses, and then of the same color that we're looking for. And then of course we need the basics for the amplification of we just want photons, any amount, and that's why it's like a rough, fast analog style that will be calculated at the GPU level, which is effectively what our displays already pretty much do. They just tell us to send it here, and so this is just a faster way to do it, without unnecessary need for it to ever be anything other than a direct, hard-coded fiber optic kind of style of matricity branch out to each individual area that happens to go like, oh, this is the information, I collapse over here, and then I go over here to the top right or bottom left or the middle, I have this amount, this kind of, level of photon release, this kind of, that kind of stuff. So it's quite fast, it's quite efficient, and it's extraordinarily simplistic to make with that kind of style of plasma, because you make cold plasma. pretty easily. If you're unaware, you can make cold plasma. It does take a bit of energy, but I'm pretty sure we've got that. And then over time, we burn so much less energy as a result that we actually make back that with our displays and our computational increase ability, because we've got more computational ability given per each transistor here. And as a result, our transistors go faster and for further, because our transistors are operating off of light. Now, with a increase effect which then gives us a pulse and wavelength effect of our given digital information for our photon release down the fiber optics, which is incredibly fast and incredibly simplistic, which is almost like an analog, but it's not. It's very much dynamic, not an analog. And as a result, we're able to program it. It just takes memory to be moved, and so these series of digital informations has a program that goes, hey, so I get converted to this light wavelength, amplitude. I already said wavelength, spin, directionality, polarization. And so that allows for a increase and more direct shots of fiber optic lines, and even combining fiber optic, wavelength to be far simpler and able to calculate far more, depending on how fast we can break it out with the analog quotation marks here, cache computer, because the cache itself is the light in a way, if you figure out how to do that, but also the oscillating frequency lines, which are far better, I think, as a way to use computational methodology to have error correcting and increased speed and encryption to the CPU. So that was my way of being able to, if I can get like a little bit of electricity from the computer to move alongside with the fiber optics, which wouldn't be impossible, I could shove it into the display and it'll go and give me all the photons that I'm looking for and everything else with incredibly high accuracy, high efficiency, and high clock rate and bandwidth for each transistor, CPUs and GPUs even. So I think it would be beneficial. And that is the John Tyler Lemke Xenon Reality patent pending concept. There you go. Bye.